Oh, yeah, my slide set is visible to you now.
Yes, sir.
Okay,
Yes, sir.
fine. So let me continue our discussion on this particular uh, concept learning. And as you know that uh, the primary objective in this learning is to learn some hypothesis in a hypothesis space to fit the training examples. So which should satisfy the training examples. And in the training examples, they are in the form of positive examples and negative examples. And in this particular task, we are trying to find out a hypothesis in the form of a Boolean function, a Boolean expression, and a particular representation that we consider uh, here, uh, as you can see in this particular slide, that the hypothesis examples are shown in your left side, whereas the hypothesis they are shown in the right side. There is a diagram which I am going to explain. But you note the uh, let me use the pen. So you know that this is the hypothesis set of hypotheses, and these are the set of training examples, and they almost look like similar. The form is like a vector, and each position in the vector is an attribute, and where they can assume certain set of values, there is attribute space. Like no, we already discussed this thing. Like this, sunny is the corresponding sky condition or uh, the environmental condition, and I think this is the temperature. There is something like wind, humidity, wind speed, and maybe the water conditions, water temperature of water, and the forecast. So these are the uh, six dimensional space, and these are the six variables or six attributes which provide you certain facts about a day. Of course, the facts about a day, and then of course there is something more which is not shown here. Some of them are positive. That means what exactly you are going to find out that given these conditions, whether a person is interested to watch sports or come out for watching sport, or maybe participating in sports. So enjoy sports. I think that was the name of the task or name of the variable which we would like to predict and which has a two value, either yes or no, right? So here we have just shown you the data point, but we have not shown that no, which one is positive and which one is negative. Those may be coming later on. On the other hand, you can see that representation of hypothesis here, and the hypothesis also consider the same six variables and represented in the form of this vector, and these are the values. If they're true, then the hypothesis, these are all conjunctive normal form hypothesis. So every hypothesis is independent here. Okay, so these are all various hypotheses, different hypotheses I should say. But there could be some relations among them, but actually they are all self-contained hypotheses. And here, for example, it means that if the sky condition is sunny and whatever may be the temperature and humidity, but the air, the wind speed should be strong, and also the water could be either cool or warm, whatever may be the conditions, or and whatever may be the forecast. Uh, Irrespective of this, I mean, all these things, if they are satisfied, then no, this hypothesis is true, which means that you are, in that case, you are saying that the person would be, a person would enjoy the sports. Now you have to find out whether X1 satisfies H1, whether x2 satisfies h1. If x1 satisfies h1, which means this is a positive example. I mean, that means this is a positive, not instead of saying example, that means given these conditions, enjoy sports is true. So we have discussed all these things. And we also told you that this kind of learning is an inductive learning, because from the positive and negative examples, you are learning this hypothesis. You are choosing a hypothesis from a hypothesis space. Now, a hypothesis space is a set of all possible hypotheses which consider this kind of form. So there are certain examples are there. Now, one of the interesting fact in the hypothesis space is that there is certain kind of structure or certain kind of order in that space. That means some of the hypothesis is more specific and some of the hypothesis is more generalized. Which means that, for example, you see that this H1 and H2, these are the two hypotheses. Now, in this case, you can see whatever example is true for H1, they are also true for H2. Because here, whether the wind speed is strong or low, weak, whatever I think those are the two values. H2 will satisfy in both the cases, whereas H1 will be satisfying only the wind, whether if the wind speed is strong. So I can say that H2 generalizes H1. Now, if I consider, say, H3, now here you can see that in H3, H3 is more specific than H2, right? Because there is a constraint on that the water temperature should be cool. I mean, you should remember that what every position means. I have to also remember. So there might be some mistake, then you can point out. So, suppose if the water is not cool, then obviously this hypothesis is not true. I mean, if the water condition temperature is warm, then it is not true. But whereas in the H2, this can be true also. That means whether water is cool or warm, it is true. That means H2 is more general than H3. Now, in the hypothesis space, some schematic diagram. It's an kind of representation which helps you in understanding these things. The thing is that this arrow denotes that a hypothesis is this hypothesis is more specific than this one. That means H3 is more specific than H2, okay, or H2 is more general than H3. So this is a relationship, but you cannot compare H1 and H3. So it's a kind of partial ordering, as you can see, and that kind of order is it is observable, that you can observe this order. So that is how the hypothesis space is organized. So if you, for example, if some hypothesis is true H1, then H2 will be true, because this is also more general hypothesis. Similarly, if H2 is also true, then this hypothesis is also true. This hypothesis is also true. That means all these hypotheses, they will satisfy the training examples. So this is the implication, and this is the implication of this ordering. And that's what I told you already, that given the set of training examples, there could be a number of hypotheses which will satisfy those examples. So it may not be unique, but there are certain characteristics that we see. So let me change to the pointer options to arrow. Right. So this is what you see, that we just mentioned, that we say a hypothesis is more general than another hypothesis, H prime, and which is denoted by this particular symbol. It should somehow in my presentation in Mac, this is one problem. I cannot highlight with the marker, so only I have to highlight using a pen. So you see that this H prime is more specific than H, or H is more general than H prime. If for every instance in H prime, if it is true for H prime, that is also true from H. So this is how you state this fact. This is the implication. So if H prime X equals 1, that implies that Hx also should be equal to 1. So if it is true, then you can say H is more general than H prime. Then you can place, suppose here it is H, so you can place H, and suppose this is H prime. So in the hypothesis space, you can have this particular kind of relationship. You can draw. I mean, that's some schematic representation of the hypothesis space. Okay. So can you tell me that which is the most general and most specific hypothesis in this particular space? What could be the most general hypothesis, and what could be the most specific hypothesis?
So a hypothesis with all
Question mark.
That is more, all question marks should be most general.
General.
Yeah, and what should be most specific?
All five.
All values.
All
values filled up.
Exactly. So all null is most specific hypothesis, right? Of course, no, it does not give any particular information, which means that in this hypothesis, nothing is true. All examples are negative examples with respect to this, or all instances will not satisfy. Every instances will be they won't satisfy for any instance. Okay, so let me change this option. Fine. So finally, as I was mentioning that in your case, your learning is a search problem where you have to search a hypothesis that should best fit examples, and also our assumptions are that the examples are error-free, and then H should satisfy all of them. There is also another assumption that your target function, that means there exists an hypothesis which should satisfy all these examples. So there exists a target function which should satisfy all these examples. So so that is kind of assumption. These are the two major assumptions, that the hypothesis, the examples are error-free, and also the target function is also part of your hypothesis space. And the other assumption I mentioned also, that the form of the hypothesis, that means it's in a conjunctive normal form, and we said that is the only form of hypothesis in your case. That is the form of the target function also. Now that is the kind of assumption. Now naturally it is not unique, as I mentioned earlier, and also not unique means several alternative hypotheses may fit examples. It may not exist any solution at all. That means it could be null also. That means no. If there are contradictions within that, it is not error. So that means your training examples are in such a way that yeah, actually there is a contradictions, and then you will get an empty space. So it should satisfy all positive and negative examples, and constraints may have in other form. So that is another thing. That means you have those examples, training examples, but your target function is not in this form. So in that case, naturally, you will not get any hypothesis, and that is the kind of empty set that you will get in that case. So I already discussed about this in my previous class, that some of the form of expressions, Boolean expressions, that we will not be able to capture. Suppose the sky condition is rainy or cloudy, and but if it is sunny, then no. Suppose you are not admitting. Now, of course, this is not with respect to our particular examples of outdoor sports, but for certain hypotheses, maybe we are trying to put that kind of constraint, and then you will not have any form which will express this kind of structure. So there are two approaches for this kind of concept learning. One is that you can search the hypothesis from the hypothesis space using certain kind of ordering. And the other approach is that you can search to find all possible hypotheses using a good representation of hypothesis space. So there are so these are the two approaches. That means you may want to have at least one hypothesis which you consider that is a kind of a good representation out of all possibilities, So some more inductive bias would be forced in that case to no. That means some other characterization. Maybe as I was mentioning that the minimal length expressions. Say there may be that kind of characterizations, that kind of no assumptions. If you put, then you would like to get that. I think somebody's microphone is not no, muted. You have to mute your microphone. All of you, please mute your microphone if you're not speaking. Thank you very much. So, and then for the second approach, you will find that, I mean, the second approach, as I said, that no, it's a kind of exhaustive enumeration kind of thing. Maybe you are not following, you are following also an efficient strategy, but the idea is that you should get all hypotheses which are satisfying this example sets. So, all hypotheses that. So the choice of the hypothesis space, of course, reduces the number of hypotheses. So this is one of the conditions for this conjunctive normal form. That means, as I was mentioning, that Boolean expressions can have several other type of functions, but there could be various other forms of target functions. But you have restricted the form of a target functions, and that's why you have also restricted the number of hypotheses or the size of your hypothesis space. So there is one particular algorithm that I would like to discuss at this point, and this algorithm is called find S algorithm. So what it tries to find is that it tries to find the least specific hypothesis from your hypothesis space, which will satisfy the training examples. Now, so the algorithm starts, it's a search following an order in the hypothesis space. So it starts with, of course, the most specific hypothesis in H. What is this? I think you have already answered. So this is that, no, all null values in your attribute sets. So that is a vector. And now what you do, for each positive training instance X, you need to modify the this H so that the H should satisfy X. Not only X, H should satisfy also all the previous positive examples also. That means H should include X. So H should be further generalized from that conditions, and that is the minimal generalization that you would look for, which will also satisfy X, which will include the the X as a positive example, as a positive instance in the hypothesis, for the hypothesis. And so in this case, for each attribute, so that this is how you do this particular kind of generalization. You check every attribute constraint AI in H, and if the constraint AI in H is satisfied by X, then you should not do anything, because no, if it is constraint satisfied, that means no, the X is going to satisfy H, at least from the perspective of the attribute AI. Now, if it is not satisfied, then what you should do, you should then include the attribute value in the hypothesis if it was null. Otherwise, if there was some other value, you simply generalize it to that question mark. That means any value. So there are three conditions: either it could be null, or a single attribute value, or the any value. So these are the three conditions. As you see, that is the constraint we imposed on the representation of a hypothesis in a particular Boolean literals. So in that literal, if you find that the value of AI is not satisfying, which means there is another value of AI which is there, and naturally this condition is not going to be satisfied with this value. So what you should do then, you should turn it, you should make it as a any value, which means that question mark as a symbol. So now of course this has become a more general one, so H should be replaced by this. Now you should do it for every attributes in H. You should do these operations, and finally whatever resulting hypothesis you get, that becomes more general hypothesis than the older hypothesis. And you go on doing these things till all positive examples are exhausted. That means you are not processing anything with the negative example. So if you have negative example, then you are not doing anything. Only you are doing for the positive example, right? And then finally, when all positive examples are exhausted, then actually you are you're outputting the hypothesis H. That means that is your result. So you see that there are certain assumptions. That means only the positive examples are given to you. I mean, whatever examples are given to you as positive in the training, that is the only positive examples. Any other example, if you put into this hypothesis, that would be negative. So that is the assumption that all other examples which are not provided as a positive example, they are all negative. Some of them may be explicitly provided, some of them may not be provided, but you assume they are negative examples. Now that is the kind of limitations of this algorithm, because as you understand that from the generalizations point of view, that fact is not there. So you might have considered them also positive. I mean, then also all these positive examples could have been satisfied. But no, this is the limitations of this example. So, I mean, I mentioned already that with negative examples, you are not doing it. And if I consider what are the assumptions, as you can see that basic assumptions of the target function should exist in the hypothesis space and no error in training examples, that is already there. But the third assumption, which is very specific to this algorithm, is that everything except the positive examples is negative. So that is the additional inductive bias that you are putting into this search process, and then you are going to get the I should say least specific hypothesis in this way. So one example is given here. You can see that we are using the similar diagram what I have shown earlier, and in the hypothesis space, the upper portion is most specific and the lower portion is most general. So just for the sake of curiosity, so this is just like a schematic diagram. Naturally, this may not be the true picture always. I mean, this is just a figurative example. Now, one of the interesting thing you see that H naught that is shown in the very topmost node of this particular graph, and H naught, naturally H naught is the most specific hypothesis, which means all null, and that has been shown here, right? So you start with that because the finest algorithm, it starts with most specific hypothesis. Then what it does, it takes an example. Now you see that in this example, you see that this is the instance. This is the instance in this space. Say this is an instance in this space that is shown here. This is an instance, just once again figuratively, and it's a positive example. That is also been given to you. That means this should satisfy, you should get an hypothesis which should satisfy the positive example. So what should be the most next specific hypothesis? Just if you generalize H naught.
X1.
X1 means no, H1 should be the same set of attributes, right? So H1 should be the same set of attributes. Right. So this is what H1. So you can find that from H naught in the diagram also H1 is shown here. Okay. So we continue. So this is now my present hypothesis with respect to the whatever training examples I had in the sequence of training examples. This is my present form of the hypothesis. Next, I will get another positive example. This is also a positive example. Can you tell me what should be the next one from H1?
Only one
third-
question mark, strong one. Yeah, the third one should be question
Third
mark.
one should be an
Third
assumption.
one should be caution.
Yeah, because you see that here this is high, right? And this is not satisfying this condition, this normal, this is not satisfying. So this needs to be generalized. But normal is also accepted. So as I mentioned that if the attribute value is not satisfied, is not the same of the attribute value shown in the hypothesis, what is being present, least specific hypothesis what you have presently. Now then this should be generalized. That means you should replace it by any value condition. So which means you will have this next will be H2, and here you can see that this particular this one is replaced by question mark. Now let us see what is the next one. Okay, next one is negative example. That means you have rainy, then cold, then high, strong, warm, change, right? This is the vector, or this is the tuple, and you have a sign, negative sign, which means it's a negative. That means you enjoy sports, that level is no. You are not enjoying sports if this is the condition, right? So what should you do? Now, naturally, what so far as you understand that whatever hypothesis you have chosen, they only satisfy only those set of positive examples. Outside that set of positive examples, they do not satisfy any other thing. Now, that is always maintained. That is the kind of property of find S algorithm. You see, H2 you have chosen, and H2 should satisfy only X1 and X2 in your instance space. None other, no other tuple. Is it clear? Right? So which means automatically X3 is not going to be satisfying. X3 is a different tuple and is not going to satisfy. So I don't have to do anything. I'm not going to. So if you find that actually it is also satisfying, then naturally it's a negative example. You need to do something. Is it clear? So that's why I'm not doing anything with this negative example. Now proceed. So that's why you can see also that your state of H3 means no next version of your hypothesis, which has been, it remains the same, which means H2 and H3 remains the same. I mean, the same hypothesis. Yeah. After that, no, you get another positive example. So you see what is this positive example? It is sunny, then temperature warm, then high humidity, strong wind, then cool water, and forecast is change. Right, and this is a positive example. So how do you modify H3 so that no to take care of X4? That means the next hypothesis version of hypothesis should satisfy only X1, X2, and X4. Only three of them.
Last two should be question mark. Fifth one should be.
Last two. Warm should be.
Okay, last two should be question mark. Yeah, because you can see that cool, there was warm. So as per the algorithm, this attribute value, it is not the same. So you have to generalize it to question mark. Similarly, the change and the value in hypothesis, current hypothesis is same. So you should do it. You are right. Is there any question to anybody who has not understood this particular computation? So you get no. This is the next question. Now, suppose this is all what you have. So you stop here. Otherwise, no, you continue doing these things. You continue doing these things, and no, you will get all other things like this only. I mean, finally, whatever final hypothesis you get, that is your result. Okay. So this is what is the computation. But as you can see that no. We can understand there are certain limitations. One limitation is that I have only one hypothesis, but there could be many other alternatives. And it is a kind of examples. We will come to those terms like overfitting of data. See, it only satisfies these three positive examples. Will it help in a general conditions? Now, suppose I may have some missing data. I may not have there is no error in my training data. but I may have some missing data. There could have been some positive examples which was not included in my set, right? But they are all treated as negative examples. So we call actually this kind of situation as overfitting. This model is very overfit model. Anyway, so it also throws out information. That means it is considering, it is not at all considering negative examples because of these assumptions. It only models the positive examples. So naturally, it is very difficult to say whether it has learned the concept, and there are several ages that could fit these training examples, and you can pick a maximally specific age in that case. So maximally specific specific age is the kind of specific hypothesis which is maximally satisfying the training examples. Now, that is the result. In fact, that is what is your result. That is the least general or maximal specific. Now, it can tell when training data is inconsistent, right? So since it ignores negative TVs. So if there is an inconsistency also, it cannot check. But what are the advantages? It is simple. Outcome is independent of order of examples, because in any order, if you consider, you can prove it also that once since there is no error, once it is satisfying a particular attribute value, either it is going to accommodate more values which are satisfying it, or that is the only value. And if it is already there, so any other value, if it occurs also, that would be satisfied. So that is the conditions. There is a formal proof is also there. You may check with the Michel's book. So naturally, the question is that is there any alternative? Like second approach, I told you that we can consider enumerating all consistent hypotheses, and there is an algorithm called candidate elimination algorithm, which is more popular in that sense because it considers all possibilities. So we will discuss that algorithm subsequently. So first, let us understand the term which we call consistent hypothesis. Now, a hypothesis is consistent if it satisfies all the positive training examples, and also all negative training examples also should not satisfy. So that is what is consistent. That means you see that Hx equals Cx for each training example. So whether Cx is positive or negative, that means 1 or 0. So all values should be satisfied for the hypothesis. Now, whatever is given in the training set, outside this training set, now it can have Hx could be any value. Now, whether actually that is a target function value or not, that is not your botheration. In fact, that is also not given to you. Only in your training examples, CXs are available only with this domain, with the training data sets only in D only. So naturally, you can only say that your hypothesis is consistent if it at least satisfying all the training examples, whatever specifications you have. So consistent with a set of training examples D and of a target concept C. So this is how a consistent hypothesis is defined. And we should note that this consistency is with respect to a specific set of training data, specific training examples. So this is what with formal notation, if you know how to represent using formally, I told you that this background of discrete maths will help you in representing this kind of rules or this kind of facts. So definition. So you can see that this is the definition part, that we say hypothesis H is consistent with respect to the set of training examples D, and of course, in the training examples there are labels which are expressed as Cx. That means the target function value. So for every examples with its levels, the hypothesis value, the functional value of the hypothesis should be same as the functional value of the target function, right? So if it is true for all, so that is what, for each training example, that is what is represented here. If it is true, then we say that the hypothesis is consistent. Now, just to supplement this discussion, that there is another term which is called agnostic hypothesis. So agnostic hypothesis is an hypothesis which also allows certain errors. That means there could be some erroneous training sample, which means that it need not be that all values should be true, all the training examples should be true with your hypothesis. If it sufficiently covers the training data, that may also satisfy your objectives. So this is that considerations I told you: overfitting, underfitting, and generalization. So we will see those things later on in this topic. Under this topic itself, we will explore those concepts later. But it is at this point, just note it that against consistent hypothesis, there could be also agnostic hypothesis, which will allow some of the training samples leveling as which can differ on some of the training samples leveling. So, but let us only deal with the consistent hypothesis in our present discussion, because as we considered that there should not be any error in the training data set. So there is a concept which is called version space. So what is a version space? Version space is a subset of the hypothesis space which contains all the consistent hypotheses. Very simple. That means with respect to a set of training example, you have a set of all possible set of consistent hypotheses that will form the version space. So now you understand that the second approach, what I told you, that when you are trying to formulate a hypothesis or find out a hypothesis with respect to the set of training examples, what exactly you are trying to find out is version space, because we would like to enumerate all possible hypotheses. So once again, this is the formal notation, is the set of H, which should be an element of hypothesis space capital H, and also it should be consistent with respect to the set of training examples. I think it's a very brief notations, but it explains everything, right? So one of the algorithm, before going to describe the candidate elimination algorithm, which is more useful and effective, but let us discuss one very simple algorithm, and it gives you the flavor of understanding what are the other options of that is a different kinds of computation. So what it says, that suppose it is possible that you can enumerate all hypotheses in the hypothesis space, because as I told you that already, due to your constraints of inductive bias, the hypothesis space may not be so large. Say only you are considering the form of conjunctive normal form, and we have already seen that how many hypotheses are possible in the 6-dimensional space, right? So if I consider a list of all possible hypotheses, then what I will do, I will simply check each one of them one by one and find out whether they are satisfying the training examples or not. So if they are satisfying, I will include them into the version space, or I will, that means that is the result I want. If they are not, if anyone is not, then no, I will simply discard it. So this is what a simple algorithm, but as you understand, it's an exhaustive algorithm. It's a brute force procedure, and it's not always tractable. So if your version space is not of polynomial order of the input side, then of course it will be quite as you say, it's not a tractable one. So let us try to understand the implications of this negative example. So when you are trying to compute to this version space, as you understand, we are also checking the negative examples, because you are not only checking the positive examples, you are also checking whether the negative examples are also satisfied with respect to that hypothesis, right? So, so find-S algorithm gives you only one hypothesis of that version space. But when you consider all the hypotheses, then no, naturally there are many other. So let us find out. So revisit these things. I will proceed using the same steps. As you see that these are the positive examples, and you did all these things. Like no, when it is negative examples, you really did not make any change. We discussed all these examples, and X3 examples, and this is H4. So now you note that, see, H4, this is the form, and whereas the X3, which is a negative, so this is the least general, and this is a negative form. So what could be a bit more general form, which can take some other negative example, which is not the not negative, the hypothesis which are still not here. That means in H4, except all X1, X2, X3, all are negative. I think there is an error. This is X4. Huh? Last one, you should note it as X4. So except X1, X2, X4, all are negative. So it is not only X3, all other examples, if you put, that is negative. So that's why it's least general. But suppose excluding X3, if I would consider also allows other hypotheses, so what other forms are possible? What could be other forms? Can you guess? Give some other form which will not include X3 naturally. That's a negative example. But no, which may allow some other non-specified examples. Can you give me one form?
Sunny, then all question marks.
Good. You can see that. Yeah. Okay, let me take. So Sunny, all question marks naturally, as you see that it satisfies all X1, X2, X3, right? They are all positive with respect to that hypothesis, and also X3 is also negative with respect to that hypothesis. But there are many other tuples, like even Sunny, Worm, then Sunny, Worm, normal, and instead of strong, I can have weak also, right? Weak, Worm, same. That is also acceptable. That is also acceptable, which is not presently acceptable by H4, right? So you have to have strong in the case of wind speed, but even the weak wind speed is also acceptable there. Is it clear? Yeah, I think someone is also trying to say some other thing. Is there any other comment? Okay, let me. Yeah,
Sir, worm and all question mark will also be one general hypothesis. The
Worm,
second attribute worm and all question mark.
I think that is also true. You are right. Right? If you make it warm and all, then also that you see that rainy also creeps in then. Rainy also creeps in then. But the problem is that you have it is not. Yeah, I think that is fine. Warm and all should be also there. Okay. That is perfect. So let us proceed then. Right? So restriction on most general hypothesis, looking at the negative sample, we will see. Yes, you see actually these are the two, Sunny all and Worm also. Here we have just shown in a glimpse. I will discuss how to compute it. That is what is candidate elimination algorithm will be doing. So so you can see that in the there are hypotheses, and there is an order. There is an order also. It's a kind of a I should not say exactly tree structure, but it's a that kind of lattice structure. So partial order structure. The most specific, I mean, I should say least specific hypothesis or maximally specific. So there are different terms: least specific, maximally specific. It is the similar one. So this S is that, and G is the least general set of hypotheses. So this is the yeah, I think it is least general set of hypotheses. Okay, so you can I'll check those terms. Anyway, let us understand this process. As you can see that any hypothesis which is at the bottom layer, those are more general than the other hypotheses which are and where the arrow is being pointed out. So we need a compact representation of the version space. So this representation is also a kind of version space. We'll find out later on that with respect to those set of training examples, this is the version space. Later on we can find out. But what is the most compact form? Compact form is that if I give you S and G, that is sufficient. These two sets, if I give you these two sets, that is sufficient to get all other hypotheses, to enumerate all other hypotheses from this form. You can get them, but by looking at G and S only, right? By looking at so what is the restriction? Restriction is that none of the negative examples should be satisfied, and all positive examples should be satisfied. Okay, none of the negative examples should satisfy this hypothesis, and all positive examples should satisfy. So that is the restriction. So with putting that restrictions by looking at G and S, in fact, you can derive all other things. So that is a compact representation. So if I can store the most and the least general boundaries of space, and then you can generalize from most specific boundaries to specialize from, you can generalize from most specific boundaries. So this is the term, right? Most specific boundaries and most general boundaries. That is, I think, better way of. So that means this is a set S. You are basically generalizing by looking at the positive examples, most specific boundaries, and you are generalizing, or rather you are making specializing, you are specializing the most general boundaries by looking at the negative examples. So in this way, you are computing, you are generating all intermediate hypotheses in a version space. And so as I mentioned, that in a version space, that is the definition, that every hypothesis should be consistent. That means should satisfy all training examples. So let me stop here today, because I found the time is almost.
Sir, please,
yeah.
Please download the attendance sheet.
Oh, thank you. I have to download it. Just let me download, and then I have something to announce also. Just a minute. Somehow, every day I am learning this downloading, and now it is coming. It just not reports anything. It simply stays silent. I hope that thing has been downloaded. Maybe I will download next. Okay. So some of you have asked some confusion that, sir, if my connection gets broken, and then if I rejoin, and while it gets broken, if you download it. So if I download at the end, in fact, I get all the history. I could get all the history that when your connection got broken, and when again you rejoined, etc. So I think that is not a problem at all. One thing I would like to announce, that next Tuesday at 8 p.m. you will have your first quiz, and first quiz will be on this concept learning till whatever we cover on Friday. So I will try to see whether I can cover the whole thing. Otherwise, whatever we cover till Friday, up to that, we'll have the, we'll get questions on them also. And the quiz will be conducted in Moodle. So it is not in MST. So in the module, you have to, there would be a specific time, and times are already set. So preset time. So time is from 8 to 9. It is 1 hour quiz. I think 8 p.m. is that additional slot I told you, 8 p.m. to 9:30 p.m. But the quiz is 1 hour. And of course, no, you have to maintain your integrity while attempting the quiz. You should not discuss anyone. You should not discuss anyone. You can check your books. That's not a problem. You can have your books with you. But no, there should not be any consultation or any kind of message passing between you. I mean, of course, no, you can always do that. And we are not going to police you. But no, if somehow we get this information, that would be little disappointing, and sometimes we may take some action. So that is the request. Please be honest. You can use your book. You can answer it. Time will be limited in that sense. You may get more questions within this 1 hour, but that is the time. And the questions will come in randomly, and you have to answer it. And so this is what about this. So now I will take your questions for some minutes, maybe another 5 minutes we can do. Yeah.
So this class test, like we have to write in paper and then upload the pictures, or you have to type it?
It is in the module, so everything should be written in the module itself.
Okay.
But you should have your paper, pen, book, etc. all all with you at that point, because you may be time pressed. So that's what I am telling you, right? So have a good preparation of that, and it's a kind of online in the sense that that is the duration only. That time only you can attempt and you can submit. That's all. If you miss it, you miss it. We are not going to repeat it.
If we skip a question, can we go back to it?
Which one?
If we skip a question, can we answer it again? Like, can we go back to it to answer again?
Yeah, Joystick, can you clarify?
Sir, can
Hello.
I clarify, sir?
Yeah,
Sir,
Joystick.
She is not here.
Joystick is not here. So who is here? I mean,
Sir,
Ankita or
I'm here, sir. Funny. I'm
oh, Funny
here.
is here.
Sir, what he is asking is.
I understand that.
Is there any...
Whether I think it is there, but no, since I have not gone through it, so I cannot right now. I cannot comment on it. Maybe we'll get back to you by Friday. Okay.
Okay, thank you, sir.
Okay.
Sir, how many questions will be there?
That also right now I cannot tell. See, we are still preparing. So roughly, I'm saying I say that 20 questions, roughly. Is it fine? And actually, I have a calendar. So once this quiz is over, then I will announce that calendar. So in the calendar, we'll be mentioning all the dates of coming quizzes. So there will be 4 quizzes. So this is the first quiz. Every quiz will have 10 marks. So I told you that there will be 40 marks in quiz. And so those dates are all on Tuesday from 8 to 9:30 slots. So we'll specify those dates in advance. Even the topics, maybe a little bit of tuning could be there in the topic list as per the progress, but that is what is expected coverage around that time. Also, there are certain three assignments you have to submit, and there would be some opening of the assignments and also submission deadline. So all of you have to be very strict. You should strictly follow the submission deadlines, because you see that it is very difficult for us to take any submission in email, because that's not systematic. All evaluation would be through Moodle. Now, if you submit through email, then it is very difficult to put all those things. And since
So will the questions be MCQ types, or we will also have to type the answer?
I cannot tell all those things. You take it that there would be questions, and you be ready to answer any kind of things. Okay. So it could be MCQ, it could be descriptive, whatever. We'll see. But naturally, it's a quiz. No, we are not going to ask you to write an essay. But we may ask you to solve a problem, specify the answer. Maybe we may ask a little bit of explanation, maybe 1 line, 2 line explanation. So I'm not sure. Once the questions are set, let us see. Okay. So any questions on this particular topic?
Sir, can you please go to slide 18?
You cannot tell me this number. Can you? I am trying. Slide 18 you told, no? Okay.
Yes, sir.
Let me see. What is this slide 18? There is a number. Okay. This is 18. Is it that slide you are talking about?
No, sir. Where the H3 is, H4 is calculated.
This
Yes,
is
sir. Yes, sir.
19.
Previous.
Yeah, that is what is 18. Yeah.
Yes, sir. Yes.
Mm-hmm.
So
Yeah.
as per H4 hypothesis,
Mm-hmm.
only X1, X2, and X4 should give positive, positive
Right.
value.
Right.
Sir, but if we consider an input like sunny, warm, high, strong, cool, and same.
High, strong, cool, and same.
Is my sunny, warm, high, strong, cool, same.
Oh, well, yeah, you are right. Actually, this is one kind of dichotomy here. So that OR logic is not there. So you are right. Yes, some examples would be still true because of the structure of the. So because we are assuming if there are more than one value is satisfying for any attribute, we are putting it any value.
Okay, sir.
So you are correct.
Yes.
But the idea is that it tries to only satisfy only those examples. That is the idea. But because of the structure of this, there are certain some ambiguity would be there.
Understood.
Any other question? Fine. So in that case, tomorrow at 12, once again, we will meet. Thank you very much.